Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello, dear students. Welcome back once again to this TV Learning Series program. I'm Teacher Patrick, as usual, and I'll be taking you through chemistry for Senior 4. If you remember very well, in the previous lesson that we looked at in Senior 4, we are talking about Unit 4, which is about the periodic table. So it's about the variation of properties of elements on the periodic table. So if you remember even very well, we started with our lesson of yesterday was about the historical background. So we looked at the historical background of the periodic table. So before we look at the lesson of today, I just want to remind you, I want us to go together, and I want to see whether you still remember what we talked about even yesterday. If you remember very well, I said that the discovery of this periodic table is one of the most important discoveries that has ever been made by mankind. It is the source of the science, this arrangement of this periodic table. It is very important. That is why we need to look at the historical background. And that's what actually we talked about yesterday. If you remember very well, we talked about, we mentioned a number of scientists that contributed to the arrangement of this periodic table that we have here. This is a very nice arrangement as you look at it. So I want to take you through what we talked about briefly, about what we looked at yesterday, for the purposes of those ones that could have missed the lesson of yesterday, so that we can go together. So we started with Antoine Lavoisier. I said I have a problem with pronunciation, but don't mind about that. So Lavoisier organized the elements that were known. Actually, there were 33 elements known. That was 1789. That was 1789. That's when he did that. He organized the elements that were known at that time as metals and non-metals. Does it make sense? According to the new periodic table, yes, it does. Because even according to the modern periodic table, we have metals and non-metals. So that arrangement is still there. We talked about after the Lavoisier, you remember I also mentioned that the most funny part of it in his arrangement is that he included light and heat with the simple elements like oxygen and hydrogen. You just imagine how heat and light were included as elements. And then he had even some other elements that he called the earth. Actually, they were compounds. The silicon dioxide, those compounds, though, the substances that exist in nature. The silicon dioxide, which is commonly known as silica. He had even the gypsum, which is calcium sulfate, and even other calcareous substances. Those substances that contain calcium, like lime, silica, and so on. So he arranged them also in that order. So including light and heat was the most funny part of his arrangement. And it actually lasted long. In 1864, by the German chemist by names of Johann Wolfgang Dobereiner, came up with another arrangement. Still, the known elements that were there, now the elements now had increased to 56. So he arranged the elements in the groups of threes. We called them what? Those who were present yesterday, if you remember. What did we call them? We called them triads. So in the groups of three threes, and he called them triads. Then that is where he formulated the law of triads. He said that when the elements are grouped in threes, the middle element has the mass which is average of the three. If you get elements like strontium, and you get caesium, strontium, and barium, that was one of the triads that he had. Strontium has the atomic mass of 88, caesium is 40, barium is 37. When you add these three, added them together, 40 plus 88 plus 137, and you divide by 3, what you get is 88. So the average mass, the mass of the barium, strontium will be the average of the three. It worked for some elements. However, some elements could not fit in this, what he so-called the triads. So some elements could not fit in, so that made it obsolete. So it was discarded. So in 1864, the British chemist by names of Newlands also came up with another arrangement where we had 8 elements. If you remember, I talked about, I asked you to look at the calendar. If you look at any date of the day, maybe it is if it is the first day of the month, and you count upwards, you will find that when you reach the 8th day, you will find that the 8th day will be in the same position as the first one you have started. Can you just try it and see? Look at any date on your calendar and then count. You can start from first, you can start from second, and you count. By the time you reach 8, you will find the 8th date will be in the same position as you started with. So he formulated the law of octaves, which is found in the music notes. So the 8th note and the first note have the same similarity, or maybe gives the same tone. So he formulated the law of octaves. But that one, the law of octaves also breaks down after caesium. So it doesn't go beyond caesium. We looked at that one also yesterday. So it doesn't go beyond caesium. So other elements could not fit in that law. So it also was also made obsolete. So when we looked at also the Ruther Meyer actually worked with, at the same time, the same year, that was around 1869 to 70. The same year when Dmitry Mendeleev also worked, that is the same year that even the Ruther Meyer also worked. So we said that he plotted, so he determined the atomic masses and densities of the elements and plotted the volume against the atomic mass. From his experiments, there was a relationship that we saw yesterday. And if you remember what happened, some elements of the same chemical properties occupied the same positions on that sketch that we looked at yesterday. Lastly, we had looked at the Mendeleev's periodic table. So today, we'll just move from Mendeleev's periodic table to the modern periodic table. So what I want also you to remember is that, or want you to note, is that these personalities I've mentioned are not the only ones that had tried to arrange the elements. There are so many of them, but we just come up, I've just picked the most important ones. But if there are some other scientists that also tried to arrange these elements. So we'll move from the Mendeleev's periodic table to the modern periodic table. Actually, this is what we are just going to look at. Modern periodic table. So look at the modern periodic table. This is the modern periodic table that we have. And then we try to compare it with the Mendeleev's periodic table, which we have here. Yesterday I talked about the Mendeleev's periodic table, where he arranged his elements according to the increasing atomic mass. That is what we said. It was increasing atomic mass, increasing atomic mass. And there is something that, that is unique to his arrangement. Even when he arranged these elements according to the increasing atomic mass, he never even maintained that principle. Because when you look at this one, if it is increasing atomic mass, you'll find, like, for example, the tellurium, which is 127, this iodine 126 should be before it should be before tellurium, but he arranged it in that position. So he put iodine in its right position. He put cobalt also in its right position. Even when he used the increasing atomic masses, he never maintained the atomic mass. So he even formulated the law that the physical and chemical properties of the period is a periodic function of increasing atomic mass. But was it maintained? The answer is no, it wasn't maintained. And therefore, that brought some discrepancies about his periodic table. So those discrepancies left some gaps. If you remember also what I talked about, what made Mendeleev, Dmitry Mendeleev, the father of the periodic table, if you remember, that's what I said, is that Mendeleev left some gaps in his periodic table. These question marks here indicating some gaps that were left. Why? When he left these, that means these elements were not known at that time. But what made him genius about this, he predicted the names of these, they predicted the properties, the chemical properties and the physical properties, the density, the boiling point, the reactivity of these elements. Even when these elements were discovered, they occupied the same position. So for example, this element after aluminium is gallium. So he called this one Eka-aluminium because that is not its real name. But when you come to the periodic table here, you will see that the element that comes after aluminium is gallium. And then he printed that one. Rather, he mentioned, he suggested that, and he was able to come up with the right conclusion. When you look at for example, if we have, here we have silicon, he left also a gap here, which was called, I called it Eka-silicon. So the element that comes after silicon was germanium. These elements, the predicted properties, both physical and chemical, fitted exactly into what he predicted in the periodic table, even after their discoveries. Now, when you look at the modern periodic table and the Mendeleev's periodic table, just have a look at both of them. What is the difference? So the main visible difference that is there you will not find these elements that we find here. These are called inert gases or noble gases. Those gases were not yet discovered, and he never included them there. So in here, you see in this one here, he had some elements like copper, like zinc. Zinc was in the same group here, these are groups, was in the same group with calcium. They had some similarity. So he had in the group 1, all the groups had A and B. So according to the modern periodic table, we still have the groups, but in the groups we no longer have according to the IUPA system. That is the international naming of these compounds that has been adopted don't have this A and B. So we still have the groups. When you come to the periodic table, we have group 1, group 2, group 3, 4, 5, 6, up to 12, and you are going up to the 18. So Mendeleev's periodic table didn't have those, these groups as it is indicated. So that is another difference. In Mendeleev's periodic table, you'll find some of the elements put together in the same group, which is not in the modern periodic table. So this modern periodic table was this table that we look at now was formulated by Henry Moseley in 1913, and a British physicist came up with the arrangement of these elements. When you look at the elements, they are arranged in increase. He arranged by that time in 1913 the knowledge of the atomic numbers, the protons and electrons were known by that time. And therefore, he was able to arrange these elements. He changed the law of the Mendeleev. Instead of the atomic masses increasing atomic mass, it was increasing atomic numbers. So when that was done, it came out in this form that we see. When you look at these elements in the periodic table, you will see that they are arranged in increasing atomic numbers. This is element number 1, element number 2, number 3, 4, 5, 6, 7, 8, 9, 10, and so on. That arrangement is in increasing atomic numbers. These figures you see, like 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and so on. Those are the atomic numbers. They are not atomic mass. So he formulated the law that the properties, so when I'm talking about the properties, these are either chemical or physical. The properties of elements. The properties of elements. So what is changing here is only the atomic mass. So the properties of elements is the periodic function. The periodic function of atomic number. Periodic function of the atomic. Periodic means repeating. So there are some, but the properties are repeated within their groups. So that is why they call it periodic function of the atomic number. That was in 1913. Unfortunately, in 1915, Henry Moseley died. He was a very young man, 27. By 18, he had already even achieved a lot. So by 27, Henry Moseley joined the Royal British Army, and he died in 1915 when he was around 27, and And on front, actually, he died on front, and that's how we missed his intelligence. And his information stopped there. Now, coming back to the periodic table, we have these values on the periodic table that we said these elements are all in increasing atomic number. So there is a way how we can determine, or before we look at that one, this arrangement is divided into blocks. So we'll see some blocks here. There is this block here. When you look at this one, this block is called the S block. That is the S block. There is this block in the middle here. You can say this is called the D block. And then there is this one here, where we see this is a P. These are called P block elements. Why these blocks? So these blocks are coming up as a result because the atomic numbers were used. So it is as a result of the arrangement of the electrons. When you have these elements in the S block, it means that the number of electrons in the outermost shell, the valence electrons, will be found in the S orbital. Just take an example of any element here. Maybe magnesium is element number 12. So what does that mean? That if it is element number 12, its atomic number will be written as 1s2, 2s2, 2p6. I hope you still remember the Aufbau's principle of how these electrons fill up in their orbitals. So they will call it Aufbau's principle. You could have looked at it in unit, I think in unit 2 of senior 4. So these are 4. When you add this is 10. Then we have 3s. We have said 12. So it is S2. These are 12 electrons. 2, 4, 10, 12. So this is why it is called the S block. The number of electrons in the valence electrons are in the S block. So in the S orbital, and therefore it belongs to the S block. Take an example of any other. Maybe potassium, because we said all this. This is magnesium. If you take an example of potassium, which is element number 19, and you write its electronic configuration, it will be 1s, 2s, 2, 2p6, 3s, 2, 3p. How many are they? This is 2, 4, 10, 12. Now 3p, 6, that makes 18. And then 3, let me see, 1s2, 2, this is 2, 4, this is 10, 12, 18. So this one will be 4s1. You remember S forms fields before 4s fields before 3d. So this is in the same, that is why we have S block. So you can write any other element here, its electronic configuration. When you are writing the electronic configuration, please remember the Aufbau's principle, the filling of these orbitals. Maybe I can just put it here. Anytime you are going to write electronic configuration, put it aside so that you don't make any error. So this is the arrangement. This is 1s, this is 2s, this is 2p. You have 3s, 3p, and then 3d. You have 4s, 4p, 4d, and 4f. So you can have 5s, you can have 5p, 5d, 5f, you can have even 5g, and so on. So this is the Aufbau's principle. And this is how it goes. So always you're supposed to, the moment you have this, you will never at one time fail to write the electronic configuration correctly. So you have to move like this. When you move like this, up to here, then go like this, and then here, then come back like this. So whichever element that you want to write, when you have this aside, you will be able to tell which you're able to write the correct electronic configuration. Coming back to this, you can easily tell we have determined the block. You can also determine from the block, you can determine the period, because we have these are periods. When you are moving that, this is period number 1, has 2 elements, number 2, number 3, and so on. By looking at the main quantum or energy levels. So this is shell number 1 or energy level number 1. This is number 2. These figures represent the energy levels. And then this is, so it means that this one is in a period number 3. Period number 3, because it has 3 shells. This is period number 3, which is here. You can even locate the group from here by looking at the electrons in the outermost shell. This one is in group 2. This one is in group 1. So you can also still tell that this is the group. Write any electronic configuration of any element and then try to see whether what I'm talking about is true. For any element that you pick from here, and then find the group. Remember, the groups that we are using range from 1 up to 18. So before I wind up, so this is all about the modern periodic table with groups and the periods arranged, the elements arranged according to the increasing atomic number. Remember the periodic law by Henry Moseley. So this is all about what we wanted to talk about, the modern periodic table. But before I leave, I would like you to take note of this homework and then try to see whether you can be able to answer these questions. So the question number 1, I will be asking you to state the periodic law according to Mendeleev, and B, according to Henry Moseley. Question number 2, you write the electronic configuration of the following elements. A, so you'll have to choose from, we can say, silicon. B, germanium. C, bromine. And indicate the block, period, and group of each element. Thank you so much for paying attention. We've come to the end of our lesson. I hope we'll be together in the next lesson, and we'll start from there. So don't forget what we have studied today. See you in the next lesson. Bye.